Hi. In this video lecture, we would be finding the specific reaction rate, right, of hydrolysis of ethylene oxide to produce ethylene glycol, right. We would be performing a batch experiment basically, right, to find K, that is specific reaction rate for this reaction, right. And why we are finding K for this reaction, because we would be doing this because we would be designing a CSTR, continuous turret tank reactor, to produce 200 pound of ethylene glycol in a year. That is, we want to produce ethylene glycol in an industrial scale, right, on a large scale, right. And so we would be developing a design equation for CSTR, right, so that we can produce or we can make ethylene glycol in the CSTR, right, because if you remember, when we were deriving the design equation for reactors, there we have a rate expression there, right, a rate law, right, R, right, and R is basically KCA, right, and this is for the reaction, right. So if we are producing ethylene glycol, we should know the reaction rate for this reaction, right, so that we can use the reaction rate in the design equation of CSTR, because design equation of CSTR involve RA, right, and RA can be found from this batch experiment, right. That's why we are doing it. So in this, just remember certain things, that water is in excess, right. If water is in excess, its concentration will remain same, right, and this value of K, the value of specific reaction rate, is constant at constant temperature, right. So we would be performing this experiment at the temperature of CSTR that we would be designing, right. So optimum temperature of this reaction is 55 degrees Celsius, right. At this temperature we would be performing this experiment to find the value of K, and when we will design CSTR to produce ethylene glycol on a large scale, we would be the temperature of CSTR would be same, right. We have been given this data, time, at various times the concentration of ethylene glycol product, right. What we have not been given is the concentration of ethylene oxide reactant at different times, right. Now since we are doing a batch experiment, right, we should know we should know the mole balance equation of batch reactor, which is this, right. Before this, just let's recall what we have done in chemical kinetics, right. We have done similar thing in chemical kinetics in school. Firstly, just see what order of reaction is this. Water is in excess, right, so its concentration will not change, right. So concentration of ethylene oxide will change. So this rate of reaction depends on the concentration of ethylene oxide, right. So what kind of reaction it is? It is a first order reaction, right. And in school chemical kinetics, we have derived this expression, it's K 2.303 upon T log R0, that is initial concentration upon final concentration. We will rearrange this equation, and on rearranging we will get log R0 upon R is equals to KT upon 2.303. T is variable, K upon 2.303 is constant, right. So if you draw a graph between this value, right, and T, right, what we used to get is a straight line like this. Here this is along y-axis, right, and this along x-axis we have T. This is a straight line, right. So this is a straight line, that means this equation must be the equation of a straight line. So if you compare it with y is equals to mx plus c, right, then slope would be m. M is K upon 2.303. So value of K can be obtained as K is equals to 2.303 into m, right. So once you know the slope of this line, you can determine K. Something similar we would be doing here, but here we have reactors involved, right, we have stoichiometry, right. So it's little different, but the basic concept is same, right, that we have done in chemical kinetics. So let's quickly look at it. Make sure you know how to make stoichiometric table, that we have done in previous lectures. You might be seeing a link flashing, so you can check if you have any doubts on how to make this stoichiometric table, because we would not be doing that in detail here, because we have already done this, right. So let's perform this experiment to find the value of K for this reaction. This is a CST, this is a batch reactor, I'm sorry, where you have fed the reactants ethylene oxide and water, right. Initial concentration is Na0 of A, right, and Na0 theta B of B, and initially the concentration of C, that is product, would be 0, right. And if you remember, we have this expression for initial concentration of B, theta B is equals to Na0, where theta B is Nb0 upon Na0. We have derived this from relative rate of reaction, from this Ra upon A is equals to minus Rb upon B is equals to Rc upon C is equals to Rd upon D. From this expression we have derived this. You can look at the previous lecture, right, for any doubts. So we have used this to reach here. So initial concentration is Na0, and this much, this is for B, Nb0, and Nc0 is 0, right. So how much have changed? Change, that means how much have reacted, which is calculated using X is equals to divided by how much of reactant have initially fed. How much have reacted, Na, how much have initially fed, Na0, right. So Na is equals to Na0x. This is the change, right. This much have reacted. This is initial, this much have reacted. So this column remaining would be initial minus how much have changed. So this is remaining. How you have calculated concentration? Concentration, we know this divided by V, right. Na0 upon 1 minus X divided by V0, you will get Ca0 1 minus X. This is concentration is, we know this number, this is what remaining number of moles, right. So Na0 divided by V0 1 minus X, it would be Ca0 1 minus X. This is how we have derived this column of concentration. Similarly, for Nb you will get this, right. Right. For Nb, this is not Nb, this is Na0, right. So you again divided with V0, you will get this. So this is how we have derived concentration terms, right. So now what we need is, this is the mole balance equation for batch reactor, and this is your rate law expression, right. So we would be using these, and input is reactants fed all at one time. Approximation, water is in excess, we have already discussed all this. Stoichiometric table, how we have made, we have discussed just now. Now we will just modify this mole balance equation. If you look at this equation, if I take this V0 below this Na0, I can make this Na0 upon, like this, Na0 upon V0. What is Na0? What is Na upon V0? What is Na upon V? Moles per unit volume. This is your concentration. So I can write this equation as dCA upon dt, which is equal to Ra, right. This is equal to Ra, right, and Ra as per rate law equation is kCa, right. So we will take this here, this is minus kCa minus Ra, right, this is kCa. So we get a minus sign here. This is, in place of Ra we will put from rate law expression kCa. So we will rearrange this equation, right, and then integrate dCa upon Ca from lower limit, from Ca0 initial to final Ca, right. Similarly time 0 to t, right. So what we will get is In Ca0 upon Ca is equals to Kt. This is your natural logarithm, right? I hope this is clear till this point. This is just simple mathematics that we already know, right? So now this can be written in the form of this. This, if you have this, can be written as this, right? This is your exponential form of this. This is mathematics, right? So Ca upon C0 e to the power of this, so just minus sign. So Ca, concentration at time t, right, is this. This is concentration at Ca is concentration at time t, which is this, right? And how we reached here? By integrating this expression, right? Just see, let's look at it again quickly. We have just rearranged mole balance equation for batch reactor, right? And in place of Ra, we have put Kca from minus Kca from rate law expression, right? This is what you have got. Just rearrange this and integrate it. You get this of natural logarithm. You can write it in exponential form, this. So this is concentration at time t, right? Now for liquid phase reaction, this you have concentration of C. What we are finding is, what we are looking at is concentration of ethylene glycol is number of moles of ethylene glycol upon V. V is equals to, we can put in place of V, we can put V0 because both are equal. It's a liquid phase reaction. So NC would be equal to, if you look at this, NC would be equal to Ca0 minus Ca, right? How you reached at this expression? From here. NC is equals to, if you look at from the stoichiometric table, NC is equals to NaX, right? Remaining is NC is equals to NaX, right? And this is NaX, right? Remaining is NC is equals to NaX, right? Because this much have reacted, so this is Na0X, right? So which is initial minus how much have reacted, that is Na0 minus Na, right? Na is number of moles at any time t. So which is your, what is remaining? Nc, right? So Nc is equals to Na minus Na0 minus Na, right? So in place of Nc, you will put Na0 minus Na divided by V, right? So you will get, in place of Ca from here, you will put the value of Ca from here, right? It would be Ca0 e to the power of minus Kt. Then you will take Ca common, then this is what you will get, Ca 1 minus e to the power of minus Kt, right? Now this, right, this, if you take logarithm of both the sides, right, it will become this is equals to Kt. What you have to do is, you just have to take logarithm of both the sides, it will become this, right? Now the situation of this has become the graph thing, right, that we have done, that we were doing in chemical kinetics, right? R0 upon R, right, here T. Similarly here you will take this in y-axis and this T in x-axis. This is the graph. Again you got a straight line, right? So this is a straight, this is, if you're getting a straight line, that means this must be a straight line. So if you compare it with y is equals to mx plus c, m is slope, right? So what is slope here? If you find it from the graph, right, slope is equals to minus k, which is 0.311 on in these calculations, right? So how will you calculate it? Using this data at time t. This is, we have been given, right, this is concentration of product, concentration of ethylene glycol. So Ca0 minus C0 upon Ca0, right? You will calculate all these from stoichiometric table, right? So you will get different values of this term, right? Natural logarithm of Ca0 minus Cc upon Ca0, which you will construct in y-axis, right? T will go in x-axis, right? So what you will get is K, right? From these values you will get slope is equals to K. If you compare it with y is equals to mx plus c, slope m is equals to minus K, 0.311. So K is your 0.311. So rate law expression will become, because this is what we have to use in the design of CSTR, because design of CSTR reactor include rate law, that is RA. So RA would be 0.311, right, per minute. 0.311 CA. This is what rate law expression is. RA is equals to KCA. K, the value of K we have found from this graph to be 0.311, right? And the value of Y is taken from the slope of this line, right? You just have to calculate the slope, right, from this, right? You have, if you look at this data, you have CA0, what we have done is, we have time and we have been given concentration of C, right? So from concentration of C, you can find the concentration of A, right? CA0 minus CC divided by CA0, right? This is what you will get, right? Initial concentration minus CC divided by CA, right? CC is given here, time is this, and then you take logarithm of this, you will get this value. All these values are constructed here, time is constructed here, right? You get a straight line, right? This straight line is of this form, y is equals to mx plus c, right? So slope is minus k. If you compare this with a straight line, right, slope is minus k here, right? So from here you can find the various values of minus k. It will come out to be 0.311. So this value can be put in the rate law expression, which is RA is equals to 0.311 CA, right? You can put this value now in the design equation of CSTR, right? I hope this is clear, right? Now in the next video lecture we will look at the design of CSTR, right? Thanks.